Let's suppose that we're designing a small application for a company that provides technical services at the customer's location. From this application, among other things, we'll be able to generate the orders for repair requests made by customers. Let's look only at the transactions we're interested in for our example. We have a transaction to record customers, another transaction to record the company's technicians, and a transaction where the materials can be recorded, which the technicians use to solve the different issues of clients. Then we have this transaction, repair order, where the operator who receives the request from the customer will enter all the necessary data to generate the service order. In it, we have as a primary key the repair order ID attribute, which has an auto-numbered data type assigned to it. Each order will have an associated client, so in this transaction, we've inferred attributes from the customer table. Lastly, we have these other attributes of the transaction. To record the date of entry, the type of order, whose data type will be enumerated containing these values, the price, a status, whose data type will also be enumerated and will accept the following values, the date scheduled, and a description. Let's look at the rules we entered. We have a couple of default rules and several no-except rules. In the default rules, we assign a value to the attribute that will keep the status of the order, in this case, P for pending. And in this other case, we'll assign today's date to the attribute that will save precisely the date of entry of the work order. We also see that this attribute, repair order price, of the transaction will be calculated from the value entered in this other attribute, repair order type, which will record the type of order. And lastly, we declare a couple of error rules. Let's see this transaction running, from which we enter a repair order. Now let's suppose that in our reality, after an order is entered, a coordinator must assign a technician to it and the materials provided to that technician in order to monitor it and change its status to assigned. In addition, when the task is completed by the technician, an administrative assistant should be able to assign an end date to the order, enter comments from the technician and the customer, record whether the issue was solved or not, and change the status of the order to completed. How can we do this? One option would be to add all these attributes to the transaction, and to complete those that we need at every moment. The transaction would look like this. Let's see it at runtime. As we can see, this solution does not provide a friendly interface for the user, since there will always be fields that may not be of interest or may not have to be completed. For example, when the operator receives the order from the customer and enters it for the first time, before it's assigned to a technician, we'll see several fields that will not be completed. In this case, they are relatively few, but if the number of attributes is increased, this will impact more and more on the users and their experience with the system. The same happens when the coordinator accesses the transaction, selects the order to be modified, and so it's changed to update mode, assigns a technician to it, and loads the materials. As soon as we search for the order and load it on the screen, we'll be shown attributes that we may not be interested in viewing. Then, to load the materials, you'll have to leave fields empty in order to complete them later. Of course, this is not comfortable for entering data. And as we've just said, since there are few attributes in this example, it doesn't have a great impact. However, as the number of attributes increases, since we may need to record more data, the input process becomes more complex. Or, when the administrative assistant wants to complete it with the corresponding observations, he'll need to select the order to work on, switching the transaction to update mode, and will see all the attributes of this transaction, when in fact, he only needs to see a few details. Another disadvantage is how complex it can be to program the behavior of this transaction. As we saw, it'll go through different states and modifications with later entries. Also, it may require different controls every time, even of the attributes themselves. But given this design, everything will be programmed in the same object. It won't be possible to customize rules or events specific to each of the moments that we've just seen. These disadvantages could be solved in a simple way by using what we call parallel transactions. In this way, we would have a transaction for entering the order first by the operator, another transaction where the coordinator will assign that order to the technician and load the materials to be given to him. And lastly, a transaction where the administrative assistant will be able to upload the technician's and customer's comments, if any, and whether the problem was solved or not. Each one of these transactions will have the attributes that we are really interested in for each case. For this, all three transactions must have the same attribute as the primary key. This is what makes them parallel transactions. It's important to mention that the parallelization of transactions is done by level. In this example, the main levels of these transactions are parallel. If we look at the rules section of the transactions, we can see that each one of them has its own rules, totally independent from one another. This is one of the great advantages of working with parallel transactions. The same is true for any events we may program. Let's see the application running with these modifications. From this transaction, repair order, an operator receives the customer's request and completes all the fields. We see that the value P, pending, is assigned automatically because it's defined in the default rule. Sometime later, the coordinator accesses this other transaction, repair order assigned, searches for the order, and completes the necessary data. The value that records the status of the order is automatically changed to A, assigned. Finally, after the task is completed and the technical report is received, the administrator will manage it from the third transaction created, repair order completed, filling in the corresponding fields, and the status will be automatically changed, assigning it the value F for finished. We see that, in this way, it becomes much simpler, clearer, and more intuitive for users, and it helps to make the application scalable to face future changes that may have to be made in the procedure for entering orders. At the database level, from the main levels of these three transactions, a single physical table will be generated, since, as we know, Genexus designs the database following normalization criteria. The generated table will contain the attributes resulting from associating the three transactions. When we enter a record from the first transaction, what happens then in the table of our database, with the attributes to which we haven't assigned any value yet? What value will they have? Empty values will be assigned by default, 0 in numeric fields, empty string in character type fields, a default date representing the empty value for those of date type, and false for Boolean attributes. Parallel transactions offer a clear way to keep in the structure of each transaction solely the information you want to work with within that program, regardless of the information in the same table that can be handled in another transaction. There is a wide range of realities that can lead us to use this type of transaction, which we'll not examine in detail in this video. For more details on this topic, please visit our wiki.